Hello. I am so excited to be talking about two recent papers in reinforcement learning, which have been making a huge splash in the field. I want to open with this quote from Kyle Corbett, who runs OpenPipe, which is a reinforcement learning platform and a startup. And he's quote tweeting one of the papers that we're going to read. And he says, understanding the degree to which RL simply upweights pre-existing behaviors versus incentivizing new ones is super important to predicting whether reasoning models will asymptote at peak human performance or shoot straight for super intelligence. And I mean, who doesn't want to know that, right? There's like this promise that RL is going to give us super intelligence, that we're just going to start from the pre-trained model, we're going to RL and all kinds of stuff, and we're going to pop out with, ASI. And I really he did a follow-up tweet, which references Jan LeCun's RL is the cherry on top, which I'd actually never heard of before. But this is the figures. This is from a 2016 Jan LeCun talk. And it's very provocative, right? If we translate this to LLMs, we'd say that pre-training does the real work. It's like the cake of the cake. And reinforcement learning, it's just like a little dollop. It's not anything. It has no power compared to like the true power of pre-training and everything you get from that. So clearly an old idea from 2016. And I think a really easy way to understand this is I would turn to Nathan Lambert's blog. Nathan Lambert is at Allen Institute. This is the Tulu series of models. And he basically has an argument from March, which says, after you're done with pre-training on internet scale data, all you're trying to do is elicit different stuff from different parts of the latent space. So this is specifically from his section on RL. Okay. The astute way to view the model learning new behaviors is not that it's learning entirely new abilities, but rather learning to reinforce behaviors that were already latent in the pre-training data set. Kyle echoes this, right? Recent papers all point the same direction. RL is mostly just eliciting latent behavior already learned in pre-training, not teaching new behavior. A third example of someone saying this comes from the CTO of writer.com. And he goes, I just read this. Does reinforcement learning really incentivize reasoning? That's the paper we're going to read. And he says, it's what our teams has suspected all along. RL isn't learning, it's alignment. It shifts distributions, it doesn't build new ones. Then when someone follows up, he goes a little further. He claims here, in simpler spaces, RL can innovate, but the LLM's vast action space need those priors to navigate. So we'll come back to this later, but this is a specific claim about, let's say you're playing Pong and you can only move your controller up or down. That's learnable. But if you're just trying to speak in natural language and you could say 30,000 next tokens at any point in time, there's too many things you could say. You could never learn. It's too big a space. That's the claim. I disagree with this claim. But anyway. Okay, so we're going to have a lot of fun. What we're going to do is first we're going to read, does reinforcement learning really incentivize reasoning capacity in LLMs beyond the base model, coming out of Tsinghua from April 2025. Then we're going to follow it up with reinforcement learning fine-tunes small subnetworks in large language models, coming out of Illinois Urbana-Champaign, May 2025. Then we're going to talk about what this all means, and I'm going to try to give some perspective. I might be right, I might be wrong. Who knows? I've been wrong about many things before. And I really want to tie it in with this AlphaGo Zero work. So because it's a little confusing, there are multiple papers that Google wrote about AlphaGo. There is original AlphaGo, and then they redid it with AlphaGo Zero. And original AlphaGo, the important part is it was trained using supervised learning from human experts and then reinforcement learning. So first they behavior cloned the behavior of top pros, and then they were like, can we do even better? That's original AlphaGo. And now AlphaGo Zero is like, we're going to start over, no behavior cloning, no human games. We're just going to use pure self-play and prove that we can get back to that same quality bar from original AlphaGo with just self-play. But the important part is this AlphaGo work is from the board game days, and now we're in the LLM days. So going back to this quote from the CTO of Writer, he's like, yeah, but like, come on, like, it's a board game. Like, you can only make like what, like 10 moves at a time, 50 moves at a time. When you're speaking, I could say any words. My action space is too big. There's no way this shit's gonna work for language models. That's the claim. Okay, so let's get started. This is gonna be so much fun. First paper, does reinforcement learning really incentivize reasoning capacity in LLMs beyond the base model? This was a really cool paper. I disagree with the conclusions, but the results are really, really cool. So what they do in this paper is they're interested in this pass at K metric. In the study, we critically re-examine the assumption by measuring pass at K. So what they're going to do here is they're going to say, if you give the LLM a problem and you run it multiple times, there's natural stochasticity, there's natural randomness in the LLM. And because of this, you might get different answers each time you run it. So if you run it like 10 times, maybe one of those 10 times it got the question right, okay? And then what if you run it like 200 times? So the main claim is basically that the RLVR trained model is just learning to choose the good paths among the paths that like it would naturally stumble upon anyway. So it's like the RLVR model isn't learning anything new. It's just like if you'd given the base model enough tries, it would have gotten there eventually. But RLVR is just like getting there quicker or getting there more often. So they have some graphs which, yeah, so let's just look at one of these graphs. So this is a benchmark, and the x-axis here is the number of tries you give it, right? So what you see is when you only give it one shot or two shots or very low numbers of shots, the RL model is more likely to get it right, right? But the more chances you give it, eventually the base model not only finds a solution, but starts surpassing the RL model. And this is kind of surprising, right? And then they do some more experiments where they roughly show that, you know, they like look at the trajectories of the base model and the RL fine-tuned model, and they're like, yeah, all the things that were actually found, we can show you which trajectories in the base model, like where this came from. We can find the same basic trajectory in the base model. Okay, so this is pretty damning evidence that the model isn't actually learning. I think this is really, really interesting. And this would align with like the things we kind of said at the beginning, you know? Oh, it's just like figuring out which of the abilities it already knows it's supposed to use, or like, yeah, it has the whole cake, but we're just like dressing it up correctly, or we're like finding the correct part of the latent space to elicit. You can see how this paper really does a pretty good job of making that case. There is one small point, which is a lot of these are small models. If you look at these 7B, 14B, 32B, 8B, so like for reference, you know, something like the DeepSeek V3, this is like 600B. I mean, active parameters versus not, but, you know, roughly like at least 10 times bigger than anything they are working with. So you got to consider like what happens when you make the models bigger. And then you also got to talk about how long are you training it for? Because generally, you know, when you train it for a short amount of time, it'll find like the easy stuff. And then if you try to train it for longer, hopefully it'll like start to find the more nuanced things. So the easiest stuff is like the problems that it knew how to do anyway if you gave it enough tries, and then hopefully if you keep training it, it'll find new things. But to investigate this is where we get to our second paper, which I really, really like. This one's honestly a really fun read. I really enjoyed this one. Reinforcement learning fine-tunes small subnetworks in large language models. Let's just go through the abstract. Okay. Reinforcement learning is really good at improving performance. Surprisingly, when you do RL, it only updates a small subnetwork comprising just 5% to 30% of the parameters, with the rest effectively unchanged. We refer to the phenomenon as parameter update sparsity induced by RL. This is weird. So they're saying when you run RL, somewhere between 70 and 95% of the weights just don't change. They're completely left alone. And what they claim is what must be happening is you can think of this 5% of weights that are being updated as a connected subnetwork, kind of like a subgraph, that you can just mess with this subnetwork and leave everything else alone, and it's all going to work out. Really, really interesting. So then they back it up really well. I really like this. They use 7 different RL algorithms. Okay. They use 10 different LLMs made by different companies. Okay. Then they do these really lovely ablations to compare it to other things. So they're okay, RL has this sparsity nature. What about supervised fine-tuning? Does that? And they show that no, supervised fine-tuning is dense. Here's the results for supervised fine-tuning versus RL. And so all these dark ones are reinforcement learning. What you're seeing here is this represents the base model. So Tulu, that's the Allen AI model. Llama comes out of Facebook. And then in parentheses, these are the different reinforcement learning algorithms. This is direct preference optimization, proximal policy optimization, group relative policy optimization, KTO, SIMPO. These are less important. But so you can see that they have a variety of model families by different creators of different sizes. This one's 7 dB, this one's 8B. These are billions of parameters. And they show that for different RL algorithms and different model sizes, you have this consistent thing or consistent pattern that when you're doing RL, right, 60 to 80% of the weights are not changed. But when you're doing supervised fine-tuning, almost all of the weights change. It's flipped, right? So in the Tulu 3 case, 76% of the weights are unchanged during RL, but only 6% are unchanged during supervised fine-tuning. So they're there's something going on between supervised fine-tuning and RL that it's a very, very different update mechanism. And it's there's something odd. Okay, let's keep investigating. So the next thing they investigate is, so a neural net has layers, right? You kind of have the input comes in, it goes through all the layers, and then it comes out the other side. And they're what if the reason that it's sparsity is it's just changing certain layers and leaving others alone? Maybe the gradients aren't back propagating all the way back to the start of the model. So you're just updating those last couple layers or the first couple layers. A good intuition here is in the image model space, right? There are these low rank adapters, LoRa's. And the whole point of a LoRa is you just train this little module that you stick onto the front of the model. So it's like an itty bitty guy that's before layer 0. But these graphs are really interesting because these graphs don't show that at all. They show, again, as you're moving through the layer index, this is from the input, then layer 0, 1, 2, 3, 4, 5, 6, 7, and then again, 35, and then output. They're showing that the sparsity is maintained throughout all of the layers, right? There's still sparsity across the whole network. And then these are the different operations in the neural network. So queries, keys, and values are part of the attention mechanism. The multi-layer perceptron is kind of between attention mechanisms. I actually don't know what O means. And layer norm's not important. So what they're saying is, and it's not just like, so this would be another hypothesis. You might be like, well, maybe the attention mechanism's not being updated, but just the feed forward part, the multi-layer perceptron is. But they're like, no, it is actually consistent between the attention and the feed forward parts. It's not like that either. So they're really making a really compelling case that this sparsity is spread out across each layer and is kind of equally distributed among these different components or modules, like the attention module and the multi-layer perceptron module. Okay, continues to be interesting. Let's keep going. Yeah, and I really like the way they do this. They have these really cute things where they like make a claim and they do a takeaway. So they like present some evidence and they like takeaway 1. RL leads to consistently sparse parameter updates while supervised fine-tuning produces dense updates. Sparsity emerges as a characteristic property of RL fine-tuning in LLMs. Cool. All right, this is the one we just did. We just explained this one. All layers and parameter matrices receive similarly sparse but full rank updates, while layer normalization params are almost never updated. Okay, so this is my favorite part of this paper, where they break down why these things might emerge. So, which factors contribute to the update sparsity observed in RL fine-tuning? And they're like, culprit number 1, maybe it's these classic regularization techniques that we use. So KL divergence and gradient clipping are 2 very common ways to try to keep your policy on the rails. So KL regularization is like, when we're doing our reinforcement learning, you can't diverge too much from the original policy. So the like probabilities of the logits you output, they need to basically stay similar enough to the original policy. And if you go too far away, then you get some punishment in the reward signal. And they're like, well, maybe this is the problem, right? Maybe it's this KL divergence, which is like why it's only updating a few things, because it's trying to keep the KL down. But they're like, to test the impact, we train our GRPO variant with and without the regularization terms, and we find that both configurations exhibit comparable sparsity levels, suggesting that neither gradient clipping nor KL regulation is the primary driver of the update sparsity. I mean, like, this is a controlled experiment. They did the exact same process with and without these regularization techniques. So gradient clipping, I forgot to explain gradient clipping. Gradient clipping is like, you want to make sure that you have kind of a smooth gradient update surface. So if the gradient is too big, like let's say that I get a giant reward, I don't want to use an absolutely massive reward to like completely change my policy. So let's say that, I'm playing a video game that I've never played before, and in that game, I like happen upon some item which gives me like 1,000,000 points, and I'm like, oh my god, this is the best item ever. I'm only going to ever try to get this item and not do anything else in this game because nothing else would even be worth it compared to how many points there are. You see how like a big reward has like completely changed my policy and like diverted my attention from like the normal way I play this game to like this whole other mindset? So gradient clipping, let me pull up PPO just to explain this. Here, I really like this diagram in PPO to explain gradient clipping. So it's like, you don't really trust that you've actually found the right answer. I really like the way they say that it's like pessimistic. So they're like, yeah, if you think you found something really good, maybe you found something really good, but maybe you don't understand the whole picture. So we're going to be pessimistic, and we're going to be like, if you think you got like 1,000,000 reward, we'll give you like +1, but not like 1,000,000. And the concept there is like, you might be wrong. And if you were wrong, we don't want to like completely wreck the policy in just for like this reward we got. So that's why they're like, especially on the positive side, if you got a positive reward and it's huge, they're like, let's just give you like 1 plus an epsilon, like 1 plus a little value. But if you're on the negative side, then it's like, we're pessimistic. So if you got a negative signal, it's like, well, you're probably wrong. But if you think you got it right, it's like, I don't know about that one. So that's your little TLDR on gradient clipping. But the important part is it doesn't do anything. In their experiment, they do the exact same model, exact same algorithm with regularization and without. And the sparsity level was 69% or the sparsity level was 68%. So, I mean, and they're also just like, SimPo didn't even have KL divergence. So, because they're doing a variety of RL algorithms, I also find this one pretty compelling. That, like, it's not looking like KL's the culprit. I mean, there's two different kinds of evidence we see. Okay, moving on. The next one we have is training duration. This is kind of what we talked about in the does RL really incentivize beyond the base model, where they just do like, if you give the first model 256 tries, it'll get it eventually, and RL is just figuring out which of those things base model already knew to prefer. One of the criticisms is that they're small models and they weren't trained that long. In fact, we can actually hear this criticism directly from Sholto Douglas from Anthropics. This is Sholto's Dwarkesh interview from May 2025. Here we go. Let's take a listen.
To suggest that we're like getting new capabilities from these reasoning models is that all these capabilities were already baked in the pre-training model. I think there's a paper from Tsinghua University where they showed that if you give a base model enough tries to answer a question, it can still answer the question as well as the reasoning model. Basically, it just has a lower probability of answering. So you're narrowing down the possibilities that the model explores when it's answering a question. So are we actually eliciting new capabilities with this RL training, or are we just like putting the blinders on them?
Right, like carving away the marbles on this. I think it's worth noting that paper was, I'm pretty sure, on like the Llama and Quen models. And I'm not sure how much like RL compute they used, but I don't think it was anywhere comparable to the amount of compute that was used in the base models. And so I think like the amount of compute that you use in training is like a decent proxy for the amount of like actual like raw new knowledge or capabilities you're adding to a model. So like my prior, at least, if you look at like all of DeepMind's research from RL before, RL was able to teach these like Go and chess playing agents new knowledge that would in excess of human level performance just from an RL signal, provided the RL signal is sufficiently clean. So there's like nothing structurally limiting about the algorithm here that like prevents it from imbuing the neural net with new knowledge. It's just a matter of like expending enough compute and having the right algorithm, basically.
Why aren't you?
Okay, so super clear, more compute. So this is why I really like this section of so we're back to our subnets paper. That's why I really like this section, training duration. It's intuitive that with more gradient steps, a model is expected to drift more from the base model. However, the thing about this small subnets paper, which was not true about the Tsinghua paper, is they include DeepSeek R0 as one of their examples of the sparsity effect. And they're like, I mean, DeepSeek seems to have been trained on a fuck ton of data, right? 8,000 training steps using GRPO. However, even though it's trained for many more steps, it shows comparable update sparsity. GRPO algorithm, base model was DeepSeek v3, RL model was DeepSeek R10. Update sparsity, 86%. So like DeepSeek R10, even though it's trained for 8,000 steps, is still only updating 15% of the weights. Which, I don't know, how would Sholto feel about the just train it longer argument given this? And like that this isn't even the lowest, you know? It's like this Mistral 7B was 76. So if you're only messing with 15% of the parameters, you know, all of these classic things like the cherry on top, the elicitation argument, they're looking pretty good. Do you see what I'm saying? It's like, if you believed what Sholto was saying here about the just train it longer, just expend more compute, then why is it that DeepSeek, which is trained, DeepSeek R10, which is trained definitely for longer, doesn't show different behavior? So This is, I think, really, really important. This is actually one of the strongest pieces of evidence and provides direct counterclaim to what Sholto says in that interview. So this is pretty interesting, right? They do another one where they are like, as they train it, what percentage of the updated weights are outside of their like claimed subnetwork? And this graph, they're trying to show that like, once you get to this tail end here, it continues to re-optimize within the subnetwork. It's not like continuing to expand the subnetwork the longer you train. Okay, here we go. While it is possible, though less likely, that all models we study, including DeepSeek R10, 86% sparsity after 8K steps, are severely undertrained, and the observed update sparsity would diminish with substantial training. I mean, as a nitpick, this is not a complete sentence. This is a clause. I think you should just get rid of the word while, then the sentence is fine. It is possible, though less likely, that so it's possible, though unlikely, that everybody's undertrained. I mean, it's a good caveat, but I just really think with the DeepSeek R10 work, you really start to question like how much you really got to train it. If like, I mean, DeepSeek R1 is kind of frontier, right? Like, I don't know, looks pretty frontier to me. So I think this is really interesting counter evidence. Okay. Now we get to the best part of the paper, which I think is so funny that they bury this like 9 pages in, because it kind of underlines their whole hypothesis. And I love that they just like throw it in the end and don't really talk about it. Let's do this one. Training on in-distribution data. Intuitively, when gradients are computed on sequences the policy already assigns high probabilities to, little update to the parameters would be needed. I think we should like make sure we understand that sentence. So when your policy already thinks a sequence is highly likely, then you don't need to update the parameters that much because it was already relatively likely. This should come up in the way that we generally do most of this reinforcement learning stuff. So let's just take a very clear example of like GRPO. In GRPO, you have a group of outputs, like you run the same model multiple times. Some of them have a different reward than others. Some of them got higher and lower reward. And then you look at the relative advantage of some members in the group over the mean of the group. And that's like your reward. But the thing you're rewarding is a sequence you just sampled directly from the model. So if you just sampled the sequence from the model, the sequence must have had a pretty high probability already assigned to it. Otherwise, you wouldn't have sampled it. Unless your temperature is at like really, really high. But I think that's super unlikely. So what is this sentence saying? Intuitively, when the gradients are computed on a sequence that the policy already assigns high probabilities, little updates to the parameters would be needed. Okay. We evaluated 2 scenarios: rejection sampling and DPO on out-of-distribution data not performing supervised fine-tuning prior to RL. Another typo here. I mean, who's doing the copy editing of this paper? Since we already learned that DPO, that's direct policy optimization, with in-distribution data induces sparse updates, while supervised fine-tuning with out-of-distribution data induces dense ones, this additional experiment can serve as a control group to isolate the factor of training on in versus out-of-distribution data. I'm just going to keep reading. As shown in Table 5, our experiments reveal supervised fine-tuning on in-distribution data produces sparse updates, while DPO with out-of-distribution data produces dense ones. So this one sentence undermines the whole thesis of the paper. Let's remind ourselves, the paper says reinforcement learning creates the small subnetworks. They say reinforcement learning creates sparsity. That's like the whole fucking abstract. But now we go to page 9, and they're like, no. It's actually, if you do reinforcement learning on out of distribution data, you get dense updates. And if you do supervised fine-tuning on in-distribution data, you get sparse ones. So it looks pretty fucking clear that where the data is coming from, whether it's in or out of distribution, is far more important than whether you're doing reinforcement learning or supervised fine-tuning on that data. So I don't really understand how you publish the paper with this title, with this finding on page 9. Maybe I'm missing something, but it doesn't make any sense to me. Okay, continuing. Specifically, performing supervised fine-tuning with Quen 7b on rejection sampled in distribution data. I don't really know what they mean by this. Rejection sampled in distribution data. I think what that means is they gave it a math problem. They kept trying to get math problems until they got one that was right. And then they did supervised fine-tuning on the answer it just gave. Does that make sense? So they have like, what's 2 plus 2? And it's like 5, 3, 3, 5, 4. And then the one who said 4, it was like, great, let's take that reasoning trace and let's supervise fine-tune you to like make sure you say that reasoning trace again. And then like that's rejection sampling because they're rejecting incorrect answers. And then in distribution data means the model, I think, produced the data. Okay, so when you do supervised fine-tuning within this method, you get 90% update sparsity. Makes sense, because the model already fucking said this output. It's like, what? It's like, you're like, say that again, and it's like, what do you need? That's already my policy to say it. I don't need to change anything. Like, more likely to say it? Okay, sure, I'm more likely to say it. Like, I already knew how to say that. Okay. In contrast, direct preference optimization on out-of-distribution data produces dense updates in some 7b model with 6% sparsity. These findings suggest that training on in-distribution data is a major driver of sparsity in not only RL but SFT. Takeaway, training on in-distribution data is the primary reason for update sparsity. KL divergence regularization and gradient clipping have limited impact. This is super, super cool. Like, to me, I feel like this whole paper, this is why I love this paper so much, because it feels like a detective story where you're like hunting down the mystery, and then like finally on page 9, they like crack the case and they like tell you the answer. They're like, oh no, it wasn't something intrinsic to reinforcement learning. It's actually about whether your data is in or out of distribution. And the problem is all of these things they test on, right? The basic method that everybody's using is to sample from the LLM, filter for the best samples, let's just go with, and then reinforce on the sample that the thing already produced. And what I keep going back to is like, I know I'm not quite using this word correct, like in the technical definition, but I just think of you got to think about arbitrage, right? You got to think about like, what marginal information are you gaining? And if you're just training it to reinforce patterns that it already came up with, you just can't expect to get any big gains, which is why it's so connected to this first paper. These people are like, yeah, when you use this RLVR thing, when you like sample, pick the best samples and reinforce those samples based on like a reward, then like all you get is reinforcing behavior you already knew. And it's like, that feels trivial because you're not like, you're just training it on itself. There's no new information. So let's continue. So then this is their table where they kind of drill this point home, where they have either supervised fine-tuning or reinforcement learning, and they show that it doesn't really matter whether you're doing SFT or RL, right? It's the in-distribution data, which is sparse, and all of the out-of-distribution data is dense. Mainly because when you're doing out-of-distribution data, there's actually new stuff to learn. Like, you're actually, like, out of distribution. You're learning new shit. So, really fun paper. And I feel like, to me, this really makes that first paper click, right? It's like, why is it just eliciting things from the base model? It's like, well, it seems like when you're doing your RL, you're just training it on in-distribution data, on a portion of the in-distribution data, sure. But you should expect sparse updates, not a lot of strong signal. If you tell it to do something, it'll be like, yeah, okay, I kind of knew how to do that already, right? It's like, it's not learning that much. So when I read this, and we're kind of at the end of this paper, they just conclude, but I think this is the real conclusion, the in-distribution data problem. So when I read this, it got me thinking about, like, where do we... Okay, so let me take a step back. So we just read these two papers, or kind of skimmed through them, and I just want to recap, go back to what people are saying about it, right? These people are like, RL is just eliciting latent behavior already learned in pre-training. Model learning new behaviors isn't learning entirely new abilities, but reinforcing behaviors are already latent in the pre-training data set. RL's just the cherry on the cake. All the meat actually comes from tree training. And back here, RL isn't learning, it's alignment. It shifts distributions, doesn't build new ones. The action space is too big. I just think all of these takes feel a little bit hollow because they're all blaming RL. They're all blaming reinforcement learning, but it's the in-distributionness that's the problem, right? So this got me thinking about, like, when did RL, like, work? And so I want to just go back and do a little bit of reading again on AlphaGo Zero, which I mentioned at the beginning, and let's just walk through the abstract, okay? Very, very brief. Longstanding goal of AI is an algorithm that learns tabula rasa, superhuman proficiency in challenging domains. Recently, AlphaGo became the first program to defeat world champion at Go. Tree search evaluated positions in neural search. Talking about AlphaGo now. The neural networks were trained by supervised learning from human expert moves and by reinforcement learning from self-play. Okay. Here, we introduce an algorithm based solely on reinforcement learning without human data, guidance, or domain knowledge beyond game rules. AlphaGo becomes its own teacher. A neural network is trained to predict AlphaGo's own move selections and also the winner of AlphaGo's games. The neural network improves the strength of tree search, resulting in higher quality move selection and stronger self-play in the next iteration. Starting tabula rasa, our new program AlphaGo Zero achieved superhuman performance, winning 100-0 against the previously published champion-defeating AlphaGo. And I pulled out the part of this paper that I found really interesting. Here we go. So here's two direct quotes from the paper, from the AlphaGo Zero paper that we just read. Policy improvement starts with a neural network policy, executes a Monte Carlo tree search based on its policy's recommendations, and then projects the much stronger search policy back into the function space of the neural network. So what they're saying is you have a current policy, you sample from that policy, and then you use Monte Carlo tree search to, like, expand all of these paths, right? And they're explicitly saying the policy with Monte Carlo's tree search is a strictly stronger function than the original policy. They say here, it's a much stronger search policy, right? You're going to take the stronger policy, which is neural network plus MCTS on top, and then project that back into the original function. You're trying to get the function, the neural network itself, to learn the combined strength of neural network plus tree search. So when I read this, clearly the tree search bit is out of distribution, right? Because, like, you know, you're actually, like, evaluating positions and going down the trees. I think that's really, really clear. It's super different than just, like, oh, just sample 10 board states and then, like, pick one and then reinforce that board state. It's like, no, you're actually using an additional function to come up with a stronger Go player and then projecting that back. So when I read this, I'm like, kind of feels like distillation to me. Because, like, you're distilling policy plus MCTS into policy. And then when the policy gets stronger, You're like, great, we'll take the stronger policy plus MCTS and distill it into policy. And you get this iterative loop where no matter how strong your policy is, it would be stronger with a little bit of MCTS. So you could also look at this as like iterative distillation, right? You have some stronger thing, you know that's strictly stronger, and you continually distill it back. And now I want to go to like this original Yu et al. Paper, which Yu et al. Is this reinforcement learning. Let's look for the word distillation. This part is crazy, dude. RL and distillation are fundamentally different. Whoa. While RL improves sample efficiency, when they mean sample efficiency, they're saying instead of getting it 1 out of every 256 times, you now get it 1 out of 4 times. So we've more likely to find the good paths. We're more efficient with our samples of getting the right answer. Good. While RL improves sample efficiency, distillation can genuinely introduce new knowledge into the model. As a result, distilled models often exhibit an expanded scope of reasoning capabilities beyond that of the base model by learning from distilled models. In contrast to RLVR-based models whose capacity merits mounted by the base model. So this is really weird. Really, really weird. Because they're drawing a distinction of like distillation is one thing and RL is a different thing. Because in their minds, it feels like they're thinking of distillation as like our classic language modeling distillation, where like I have GPT-4 and I'm going to ask it for answers and I'm going to train Llama 1 billion, right? Like a very, very tiny model to copy all the answers of GPT-4. So I'm distilling from GPT-4 into a very, very tiny model. That's like our classic distillation in the world of LLMs. But I'm not sure why you wouldn't count this as distillation too, right? I have a policy at time t plus MCTS, and I distill it back in the policy, and I do that iteratively. It's just iterative distillation. So I think the concept that they're saying like distillation is a thing is really missing like why we like RL. The whole concept of RL is we take strong functions and hopefully we can find a self-guided process to always come up with a stronger function than your current baseline, right? And then distill it back. So I actually think that where I'm going here is that distillation, I think, is the key to all of this. And like that's what I'm saying. Like distillation has now become like a nothing term. But really you want to find something stronger than what you currently know and push that stronger thing back into the model. So, you know, if you just sample, maybe you'll get lucky. And maybe if you just sample and you get lucky and you do that over and over, maybe you'll get somewhere. But like, let's think of some basic examples of distillation we might come up with, okay? One basic idea of distillation would be, you have a language model, and maybe if I prompt the language model in a particular way, it does better than the baseline of the task. Sounds reasonable. That's why we have prompts. So then why don't we train it, the base model, to do what the prompted version said, right? We're now distilling from a prompted version into the base model. Okay. So maybe if you want to solve a task, you could set up a loop that says something like, can you propose a prompt for yourself? Then you run yourself with that prompt. Then if it worked, now you distill back, right? And then you come up with a new prompt. So this is a pretty nice loop because you're not just sampling from the base policy and trying to reinforce the sample. If you do that, you're just going to end up with this sparsity. You're just in distribution. But maybe just adding a prompt or having it give itself a prompt is enough to get out of distribution. That's one idea. I think if you look at AlphaEvolve, I didn't really catch this my first time at AlphaEvolve, but some people pointed it out, and I think it was interesting. Here's a part that I kind of missed. Meta prompt evolution. Instructions and context suggested by the LLM itself in an additional prompt generation step co-evolved in a separate database analogous to the solution programs. Interesting. Not really clear what that means. But the interesting thing is these graphs where they're like, if we don't let the LLM come up with its own prompts and like evolve the prompts that it's giving itself, it doesn't do as well as the full method, which surprised me. I would say that's pretty surprising. Right? AlphaEvolve uses meta prompts in order to improve the prompts that are provided to the language model. This allows it to potentially surpass the performance one could obtain using a human prompter. To test the efficacy of meta prompting, we disable it for the task of temper decomposition. Refer to this as no meta prompt evolution. So this approach from Google, this isn't like a RL algorithm. They're not pushing the gradients back in the model, but this is similar to kind of, I feel like, what I was just describing, where like, how about LLM plus prompt might be stronger, right, in the way that AlphaZero uses the word, right, the stronger policy than the policy given by the model alone. And maybe you can kind of use that as a loop to like continually distill that back into the thing itself. Okay, let's go with another idea. Another idea I had was, I mean, this is another obvious idea. I'm sure everyone's had this one. But like, let's say you have a rollout, you know, and you got the answer wrong. So I give a problem, like solve this math problem. It has a chain of thought rollout. It's wrong. And then you ask the language model afterward, why don't you go look at this answer and like tell me like what you don't like. Were there any words that you think were good? Were there any phrases you thought were not good? Right? Which is kind of like LLM as judge to self-assign rewards and positive and negative rewards about an answer it just gave. Okay. So what I at least like here is maybe by first running the sample and then running the judgment step, you might get some arbitrage that like you're slightly out of the distribution of like just what you would have sampled directly from the policy. So I just think both of these concepts, really what we're trying to do is we're trying to find ways to construct a stronger policy than sampling from the language model plainly, and using that stronger policy as an arbitrage opportunity to actually train something out of distribution into the model, right? Going back here. We want to get out of our in-distribution data. That's the whole point. If we just stay in distribution, we're only going to reinforce things we already know. We're only going to just like elicit latent behaviors, right? We're just going to put the cherry on top. All these things that everyone is saying. But I think what they're missing is like distilling a stronger model into your current policy is what the success that we've seen with RL. Okay. So, the other thoughts, as I said at the beginning, I could be right about the stuff. I could be wrong. I don't know. I had a lot of opinions about RL and ML in the year 2018, and most of them have been wrong. So just like as a prior, I'm not usually right. I remember reading the Transformer paper and like going through the keys and values and was like, this is interesting, but what's the likelihood that everything really needs to pay attention to everything else? It's probably there actually is some natural locality in the data. What the fuck did I know, right? So, like, take this all with many grains of salt, but I just want to share one perspective about distillation, in distribution, out of distribution, and kind of in the context of these two recent papers and all the discourse that's been going on. I do want to reiterate, they're both pretty good papers. I really enjoyed them. I especially think this one's super fun to read, the small networks one. And I also think that the Tsinghua paper, the base model, it's also a good read. And I think it's like pretty compelling in the like evidence that they show. So we'll see how things go, but hopefully you learned something or got some food for thought about the great wide world of RL. And I mean, I'll just go back to the start and I'll just leave you again with this Kyle Corbett quote, which is like your perspective on this of like, is it going to asymptote or is it going to go superhuman? And like a lot of the skepticism you're seeing around current RL, I just think it comes back to like, it's this in distribution out of distribution data problem. Like, if you just stay in distribution, you're only going to be able to pull things out of the pre-training corpus. But we've seen in AlphaGo Zero, that like distillation is really I would claim, a good way to think about RL. So, have a good day.